So welcome to the second part of the today's session. So the next talk is by Pierre Gabriel from Versailles University, and he worked with Grégory Dumont, and it's somehow related to the first talk, but instead of particles, we're considering gas, and of course equations are not the same, and but it's interesting to see these two talks together. So Pierre, I give you the floor.
Thank you, Benjamin. Thank you for the invitation. So indeed, I will talk about a PD model for the activity of a neural network. And before, so the neurons in this network are what we call leaky, integrate, and fire. So I will start by briefly explain what is a leaky, integrate, and fire neuron, and then derive formally without any theorem the PD that I will study. So a leaky, integrate, and fire neuron is a neuron which is structured by its membrane potential, and if we normalize this potential V to be between 0 and 1, right? The dynamics is given by this stochastic differential equation. So we have different parts here. So the first one here is an ODE, which represents the leaky part, meaning that the potential relaxes exponentially fast toward the resting potential, which is 0 in this model. And on the contrary, when you receive spikes from outside, the potential will undergo some positive jumps with length h, and this happens at times ts, which are the times at which the neuron receives spikes through the connections, through its connections. And if the jumps are in enough number, the potential can cross a threshold, which is here the number 1. And if V becomes larger than 1, then the neuron fires, and its potential is reset to reset potential VR. Okay, so if the typical dynamics of such a neuron is is given here. So we have 3 different parameters of the Poisson spike train. So if the parameter is small, there are not a lot of spikes received by the neurons, and we can see here for each spike we have a jump in the potential, and between the spikes, between these jumps, the exponential relaxation to 0. And when the potential reaches 1, it fires, and the potential is reset to a smaller potential, which is here a VR close to 0. And if we increase the parameter of the spike train, we increase the number of jumps, and we increase the number of firing events. So we want to put this kind of neurons together in a network, so they are now connected each other, and when one neuron fires, it emits a spike to the whole network, and the other neurons which are connected to him will receive this excitatory potential. So now we have a system of stochastic PDEs. Vi is the potential of the neuron's I, and now the spikes are emitted either by outside from the network, or by other neurons which are connected to I. So the arrow J to I means that the neuron J is connected to I and sends to him a spike. And if again, if Vi becomes larger than 1, then there is a firing event, and the potential of the neuron I is reset to VR. And it happens at the time which is now TSI, meaning that at this time, the neuron I emits a spike. So it's a system of particles. It can be seen as a system of particles in interaction. And we want to describe this large system by means of a population equation. Just before that, for this kind of system, here it's a numerical simulation for 100 of neurons connected. We can plot the times of the firing events. So each point is so in abscissa we have the time, and in the vertical we have the number of the cell, and each point represents firing event. So the first picture is for not that much connected network, so we can see some kind of asynchronous behavior. And if we increase the connection between the neurons, we can see appearing some synchronizations, which are the vertical lines here, meaning that at these times a lot of neurons in the network are firing at the same time. So to describe this kind of activity, it was proposed by Omurtag, Knight, and Sirovic in 2000s, a model of a population model, which means that it's kind of a hydrodynamic limit, but it's formal derivation. So they define the function sigma 0 of t, which is the external arrival rate. It counts the number of spikes that arrive from outside to the network at time t. And this is represented with these brackets here. These brackets are a kind of mean, an average over a lot of experiments. Okay, it's not a derivation of population equation in a large number of neurons. The number of neurons is fixed, and they consider a number of experiments, replicas of the network, and they take the average over these replicas. So formally, they define this sigma 0, and they do the same for the network firing rate, R of t. So again, we count all the number of firing events in the network. So now we sum. So in the previous line, 0 means that it's from outside of the network, and in the second line, J different from 0 means that the spikes are emitted by other neurons in the network. So with these two quantities, they assume that a neuron in the network feels, on average, an impulse rate, which is the sum of two terms. So sigma of t is sigma naught of t, which is what arrived from outside of the network, plus the global firing rate of the network, R of t, multiplied by a parameter j, which represents the average number of connections in the network. So we have at time t, R of t spikes in the network, and we multiply this by the number of connections between of one neuron in the network. Okay. So from that, they derive a PDE model, which prescribes the evolution of a probability density P of TV for finding a neuron in the network with the voltage V at time t. And this probability density satisfies the transport PDE, very similar to a kinetic equation. So the time derivative here is complemented with a transport term with negative sign, which means that this represents the leak current, the fact that the potential, if there is no spike receptions, will spontaneously relax to 0 exponentially fast. So it's this arrow here. And we have also some positive jumps with the rate sigma of t. So sigma of t is the jump rate in a sense, which is exactly the sum of the two terms we defined just before. And so these are the jump of size h, and the source term here represent the firing event. So when we count the number of neurons which fire, and when they fire, their potential is reset to the potential VR, the reset potential VR. So R of t in this model is you will have to count the number of neurons that fire at time t, and it's the jump rate sigma of t multiplied by the number of neurons which have potential between 1 minus h and 1. Okay, if the potential is between 1 minus h and 1 and they fire, they undergo a jump of size h, and necessarily they will cross the threshold 1. Okay, so this is a nonlinear equation. And sigma of t depends of R of t, and R of t depends of sigma of t, but this can be easily solved. These two equations, we can explicitly compute sigma of t as a function of the solution of the PDE, P of t v, the integral of the solution between in the interval 1 minus h 1. And it's important to notice here that if the connection parameter j is larger than 1, there can be the denominator can vanish, and it will lead to some blow-up effect. So what was known on this PDE before I started to work with Grégory Dumont? It was a theorem by Grégory and Jacques-Henri. So they proved that if the initial condition P0 satisfies exactly the condition which ensure that the denominator here is strictly positive, then there exists a unique solution with maximal time capital T. And this maximal time is either plus infinity or it is finite, and when t goes to this finite time t, the firing rate R of t blows up. They also prove that if j is strictly less than 1, then t is necessarily plus infinity, because if j is less than 1, it is easy to see that the sigma t cannot blow up, the denominator cannot vanish. And if j is large enough, and also sigma 0 is large enough, then the maximal time is necessarily finite. That means that all the solutions blow up in finite time. So what we want to do in this talk is to analyze the long time behavior of the solutions when the solutions are global. So so the video doesn't work here. So this is the initial condition. It's a Gaussian here, and if we can see the movie, it evolves and it seems to converge to some stationary distribution. So this is what we want to prove. Okay, so we start with the case of a network which is not connected. It corresponds to the connection parameter j is equal to 0. And in this case, the population is not a network. It's a population of individuals which are not connected together, similarly to what presented Isabelle before, when the particles doesn't interact. So in this case, the equation is linear. The sigma of t, the nonlinear parameter sigma of t, is now a constant, sigma 0. And this this linear equation generates a weakly star continuous semigroup on the space of sign measures that we denote by m of the interval 0, 1. This means that the solution at time t is the initial condition P0 transported by the operator mt. And this semigroup is stochastic. Okay, we are interested in the evolution of probability density. So if the initial condition is a probability measure, I mean, a positive measure with mass 1, then it is so for all time t. So the first proposition is that for this linear equation, there exists a unique invariant probability measure, which is exponentially stable. So for any initial distribution mu, any measure mu, the solution to the equation converges exponentially fast to mu bar, and the convergence, the parameters in the convergence are explicit. We can compute them. So the proof is based on the quite standard Doeblin's contraction argument for stochastic semigroups. So I want to take some slides to explain briefly this argument, which is very simple and very efficient, as we'll see. So Doeblin's contraction is what we are interested in is to prove that the semigroup for some time tau, so there is a time tau such that the operator m tau is a contraction in the classical sense, meaning that mu m tau minus mu tilde m tau in total variation, the distance between these two solutions at time tau is strictly less than the distance at initial time.
So the semigroup is not linear.
It's linear. It's linear. We are in the case of linear, so it's the unconnected case, and now it's linear. So we'll prove this is a completely linear theory. So if we are able to prove this, if we have that in the classical sense of contraction operators, m tau is a contraction in the set of probability measures with the total variation distance, then the Banach-Picard fixed point theorem ensures that there exists a unique invariant measure, which is exponentially stable with a rate which is explicit in terms of the contraction rate k. Okay, so we have all the conclusion if we are able to prove that m tau for some tau is a contraction. So what does it mean for probability density or probability measures? We take, for instance, two probability measures with disjoint support. So the distance between them is equal to 2 here, and we want this distance to decrease, and the only way to make this distance decreasing is to have some overlapping of the distribution after a time tau. Okay, so this overlapping in red here will give the rate of contraction. Okay, here if the k will be 1 minus the mass, the common mass of the two measures, mu tau and mu tilde tau, and we want this to be uniform in mu and mu tilde. So the Doeblin's ID is very simple. It's a criterion which is a positivity criterion, which say that if uniformly in the initial distribution mu, after a time tau, all the solutions are above some reference measure c times nu. Okay, so it's a positive measure with mass c. Nu is a probability measure. Then we can see easily that if we have this, applying this inequality to mu and mu tilde, necessarily the red zone in the first picture will be will have a mass larger than c, and then we will have a contraction with parameter 1 minus c. Okay, so this is the explanation of Doeblin's ID. So this is the Doeblin criterion. If we are able to prove this, then we will have all the conclusion we want. So this is with drawings, and if we want to make the computations, it's not easy either. So we start with Doeblin's condition. We assume that there is c and nu, so a reference measure nu, and a constant c, such that for any initial distribution mu, after a time tau, mu m tau is larger than c times nu. So now we take two probability measures, mu1 and mu2, which corresponds to mu and mu tilde in the previous slide. And we define mu as the difference between mu1 and mu2. So if they have disjoint support mu1 and mu2 are the decomposition, the AN decomposition of the measure mu, but if their support is not disjoint, we can decompose mu as the positive part and negative part, and mu plus and mu minus are mutually singular. And now we use this Doeblin condition. We apply this to the measures mu plus and mu minus. They are not probability measures. They have a mass m, which can be 1, but can be also smaller than 1. And multiplying by m the Doeblin's inequality, we get that for mu plus and mu minus, we have this inequality. And then we compute the distance between mu1 m tau and mu2 m tau. So first we replace mu1 and mu2 by mu plus and mu minus, by definition of mu plus and mu minus. Then we remove and add cm nu. So we subtract cm nu to the first measure mu plus m tau, and we subtract also cm nu to mu minus m tau. Using the triangle inequality, we get the second line here. And now, using Doeblin's condition, we know that both measures in the two norms are positive. So since they are positive, their total variation norm is equal to the mass. So we only measure the mass of mu plus m tau. So X is the state space on which we work. It's 0, 1 in the case of the Leaky integrated fire model. And since m tau is stochastic, the mass of mu plus m tau is the mass of mu plus. Here we have the mass of mu, which is equal to 1 times c and m. The same for mu minus. We put all of these together and we get at the end 1 minus c times 2m. And 2m is the mass of mu, okay? Because mu plus is of mass m, mu minus also. It is the Jordan decomposition of mu, so 2m is the mass of mu. So it is also the mass of the total variation of mu1 minus mu2. Okay, so we have a contraction in total variation distance. So now, if we are able to prove this Doeblin condition for the Leaky integrated fire model, then we have the proof of the proposition. So what we can prove is that this inequality is true for some constant on which I won't give the details of this constant, but the reference measure on nu is the uniform measure on the interval h/2 and h. And the time tau is log of 4 over h, and I will explain why. So what we want to prove with this inequality intuitively is that for any initial potential of the neuron, the dynamics can send the potential of this neuron uniformly in the interval h/2h after a time tau, which is log of 4 over h. So tau is the sum of two terms, tau1, which is log of 1 over h, and tau2, which is log 4. So the idea is during the time tau1, we consider that we estimate the probability that the neuron doesn't jump. We only keep the leaky part of the dynamics. So there is an exponential relaxation to 0, and if we do this exponential relaxation during the time tau1, then necessarily after the time tau1, the potential will be between 0 and h. So after this time, all the particles of the neurons have a potential in this small interval. And then during the time t2, we prove that using one jump, we can reach uniformly any position between h/2 and h. So the idea is we only have to consider the two extreme cases. If after a time tau1, the potential is h, and we during the time t2, we do first one jump of length h, we go to 2h, and then during the time log 4, we use the transport term to divide 2h by 4. So we reach h/2. on the contrary, if we start by using the transport term, we go from h to h over 4. And then if we make a jump h, we go to 3h over 4. So we can reach, playing on the time of the jump between these two extreme cases, we see that we can reach all the position between h over 2 and 3/4 of h. And now if we do the same for initial position, which is 0, so if we do one jump, we go to h, and then during log 4, we go to h over 4. And if we start by using the transport, since 0 is an equilibrium, we stay in 0, and at the end of T2, we do one jump, we go to the potential h. So again, we are able to reach any potential playing on the time of the jump. We can reach any potential between h over 4 and h. And we can see that this is for initial position h and initial position 0. And we can see that in both cases, we can go in any position between h over 2 and h. And by interpolation, we can be convinced that we will be able to reach the interval h over 2 and h for any initial position. Okay, so I will stop with the linear equation, and I will now prove how we can get results for the nonlinear equation. So now J, the connection parameter, is strictly positive. So we have to give a sense to the notion of solution to the equation. So it's essentially the same as for an extension of the linear case. So we ask the family of measures mu t to be weakly star continuous, the corresponding quantity, jump quantity sigma t has to be positive and locally integrable. And the equation is that if we test the solution against a smooth function f at time t, it's the solution at time 0 plus the integral in time, so it's a mild definition of the solution, of mu s times an operator a sigma s applied to f. And a sigma is the dual operator of the one which appears in the PD. So it's we recover here the leaky part, the exponential relaxation to 0, the jumps from v to v plus h, and the f of VR represents the reset to the potential VR. So there is a theorem which says that for j strictly less than 1, there exists a unique global solution in this sense to the Leaky integrate and Fourier equation. And now we will look at steady states for this equation. So if we want a steady state, we want a measure mu bar such that mu bar against a of sigma bar is equal to 0. Okay, so this is the definition of steady state, and the sigma bar here has to be related to mu bar with the same relation as before. Okay, so we want to prove the existence and eventually the stability of such quantity. So the theorem is that if J, so just before stating the theorem, I will come back to another one before. So here you have to remember that if J is large and sigma 0 is large, all the solutions blow up in finite time. That means that there cannot be steady states. So now, if J is large but sigma 0 is not large, we can prove that there exist at least two steady states. If J is not that large, there exists at least one steady state. If J is small enough in a quantified way, this constant is quite small because it's h over 4 to a power, then the steady state is unique and globally exponentially stable, very similarly as in the linear case. So how we prove the existence of steady states? So what we have already proved in the linear case is that for any fixed sigma, okay, so now we we take any parameter, which was sigma 0 in the linear case, but we can name this parameter sigma. So we have proved that for any sigma positive, there is an invariant measure mu sigma, which satisfies mu sigma tested against a sigma of f is equal to 0. The problem is that the mu sigma is not necessarily related to sigma with the relation that we want. So the question now is to find a parameter sigma bar positive such that sigma bar is indeed given by the expression here, the ratio of sigma 0 and 1 minus j mu sigma bar. So this is the relation between sigma bar and the invariant measure mu sigma bar. We want that this relation is satisfied to have an equilibrium to the nonlinear equation. So this is equivalent to equalize two functions. So we define f of sigma, the mass of the invariant measure mu sigma on the interval 1 minus h and 1. And this depends on the solution of the equation. And another function g, which is explicit and given by this expression. So to equalize these two functions, we need some information on the function f, which is not explicit. What we can prove is that this function f is continuous. It vanishes at 0, and more than that, we can say that it is less than a line with slope 1 over 1 minus h. And we are also able to compute the limit when sigma goes to infinity of f sigma. So with this information, we are able to prove the existence of steady states. The function g is so it is explicit. It goes to minus infinity when sigma goes to 0. It vanishes at sigma 0, and the limit when sigma goes to infinity is 1 over j. So now the function f is not explicit, but we can be convinced easily that at 0 it is 0, because 0 sigma is equal to 0 means that there is no jump. Okay, the sigma is the parameter of jump. So if there is no jump, there is only the leaky part, and so it means that there is only the transport towards 0. So the invariant measure has to be a direct mass at 0. So if the invariant measure is direct mass at 0, the mass of this direct mass at 0 between 1 minus h and 1 has to be 0. And when sigma goes to infinity, it's the contrary. It's the leaky part which becomes negligible, and it's everything is as if we have only jumps. And if we have only jumps, when there is a firing event, the potential is reset to VR, and from VR we go to VR plus h, VR plus 2h, etc. So the invariant measure has to be a combination of direct masses with interval h between two of them. And now we want to estimate the mass of this measure on the interval 1 minus h and 1, so the number of neurons which are likely to fire if they jump. So in this interval, we have only one direct mass. So the mass of this direct mass is 1 divided by the number of direct masses. And 1 over the number of direct masses is exactly 1 plus the integer part of 1 minus VR divided by h. So if this limit is less than 1 over j, we can easily see that by intermediate value theorem, there exists at least one intersection of the function f and j. Okay, so this is for j, not that big. Now, if j is larger than the same constant, it means that the limit of f is larger than the limit of g. If we want to have intersection, we use now that f not only goes to 0 at 0, but is below the line sigma divided by 1 minus h. And now if sigma 0 is small enough, we can see that the red curve will cross the line sigma over 1 minus h at two points. And since f is below this line, f also will cross g at least 2 points. So we'll have at least 2 steady states. Okay, I don't know how many time I have now.
How many time do you need?
Not that much.
Yes.
I can.
No, you're good. You're good.
Okay.
Yeah. It's up to you. It's up to you, really.
Okay,
You have 10 minutes is okay. Up to 10 minutes, it's okay.
okay, very good, very good.
Okay.
So now we have the existence of 1 or 2 or more steady states, and we want to analyze the stability of this steady state. So the only thing we're able to do is a perturbative argument. So when J, the connectivity parameter, is small enough, we know in this case that there exists at least one steady state, okay, because it is a particular case of this case. And we write the generator A sigma of t as a perturbation of the linear operator A sigma bar. And the perturbation is explicit, it's bounded, and it depends on t only through sigma t minus sigma bar. And we can compute this the absolute value of this difference sigma t minus sigma bar, and it's dominated by a constant times the total variation distance between mu t and mu bar. And this constant is small when J is small. Okay, so this means that the perturbation of A sigma bar will be small if J is small. And since we have proved that A sigma bar is a linear equation, okay, it's what we proved in the case when J is equal to 0, it was A sigma 0, but here is A sigma bar, it's the same. This operator is exponentially stable. And if the perturbation is small enough, the exponential stability will be preserved. We can, using writing down the Duhamel formula corresponding to this splitting here, we can absorb the perturbation inside the exponential stability of the linear case. So it is a standard perturbation argument, and we can quantify J small enough so that the sigma bar, the equilibrium is unique and exponentially stable. Okay, so these are the results we have obtained, and now for finishing, I will make links with other models of leaky integrate and fire models. So I will consider that the jumps, the size of the jump h is small, and I will define a new jump rate sigma tilde, which is h times sigma. And if we do that, we can approximate the jumps by the derivative of p of tv, derivative v. And we can also approximate the integral of p between 1 minus h and 1 by the value of p at the boundary 1. So formally, we can approximate the leaky integrate and fire equation with jumps by a purely transport equation, which is given here. And the problem with this equation is that it's a pure transport equation. So either sigma tilde of t is larger than 1, and in this case, the transport is always positive. So the particles, the potential goes to the right. It goes to 1, and when it arrives to 1, it is sent it is sent to the reset potential VR due to these boundary terms. And we have this kind of cyclic behavior, which is not that interesting and not very representative of what happens in a neural network. And if sigma tilde of sigma tilde of t is less than 1, it is even worse, because in this case, at the right of the interval, the transport is negative, and in this case, no neuron can reach the firing rate 1. And what will happen is that the solution will concentrate in a direct mass around sigma tilde of t. So this is not a very good model for describing the activity of the network. So what we can do is keeping the second order term in the expansion. When we approximate the jumps by the derivative, we can also keep the second order term with the second order derivative of p. And also in the integral, we can keep the second order term. If we do that, we have a Fokker-Planck equation, nonlinear Fokker-Planck equation. We need some boundary conditions. So in one, we take directly boundary condition because there is no. It's an absorbing point. When the potential reaches 1, the neuron goes to VR. So it's the density has to be 0 at this boundary. And we get this kind of transport equation with diffusion. And the jump rate sigma tilde is given explicitly as the ratio of a constant and an expression which involves the derivative of the solution at the boundary 1. Okay, so p of t1 is equal to 0. P is positive, so this derivative at 1 is negative. And we can see that it, again, similarly as in the case with jumps, this term can blow up in finite time. And it actually happens. So this model was studied before the model with jumps. So here I have I had a movie to compare the evolution of the two models with jumps and diffusion, and we can see that they behave essentially in the same way. So this model was studied before our work by Maria José Cáceres, José Antonio Carrillo, Benoît Pertam, Delphine Saller, and Didier Smets in some few papers. And they used entropy methods and Poincare inequalities to prove a list of results, and we can compare these results to the results for the model with jumps. So for this diffusive model, the main difference with the case with jumps is that for any connectivity parameter positive, there exists blowing up solutions. So for the jumps, if J is less than 1, all the solutions are global, so there is no blowing up. But it is very different for the Fokker-Planck equation, for which we can always build blowing up solutions. For J small, there exists a unique steady state, as in the case with jumps, but it is only locally exponentially stable, of course, because there exist blowing up solutions. So the stability cannot be global. And in the case with jumps, it is global, which is another difference. The third point is very similar to what we obtained. For G intermediate, there exist at least 2 steady states. And they prove that for J large enough, there is no steady state, which is also the case for the model with jumps, because for J large enough, all the solutions blow up in finite time. Okay, and that's all. I will stop here. Thank you.